Welcome to day 7 of Master AI in 30 days. So far, we've explored supervised learning where models learn from labeled examples and generative learning where models learn underlying data distributions. Today, we enter reinforcement learning, learning through interaction and rewards. Reinforcement learning represents a fundamentally different paradigm. Instead of learning from labeled data, an agent learns by taking actions in an environment, receiving rewards and penalties, and gradually discovering policies that maximize cumulative rewards. This mirrors how humans and animals learn through trial and error, experience, and feedback. Reinforcement learning powers some of AI's most impressive achievements. AlphaGo defeated the world's best Go players. AlphaZero learned multiple games to superhuman level by playing itself. Robots learn manipulation and navigation. Autonomous systems make sequential decisions in complex environments. Recommendation systems optimize for user engagement. Today, you'll understand the fundamental RL framework: states, actions, rewards, and policies. You'll learn value functions and policy optimization. You'll explore Q-learning and policy gradient methods. You'll understand exploration-exploitation trade-offs. And you'll see how RL powers real-world applications. By the end of today, you'll understand decision-making under uncertainty, optimal control, and sequential decision-making. You'll grasp the principles behind systems, learning to play games, control robots, and optimize complex systems. Let's explore the learning framework closest to animal intelligence. Here's exactly what we'll master today in reinforcement learning. First, we'll understand the core RL framework. Unlike supervised learning's static dataset, RL involves dynamic interaction. An agent observes a state, takes an action, receives a reward, and new state, and repeats. This feedback loop is fundamental. We'll formalize states, actions, rewards, transitions, and policies. Second, we'll learn value functions, estimating how good states or state-action pairs are. The value of a state is the expected cumulative future reward from that state. Computing value functions enables finding optimal policies. The Bellman equation expresses this recursively, enabling dynamic programming solutions. Third, we'll master Q-learning, one of the most important RL algorithms. Q-learning learns state-action values, estimates of action quality in each state. From Q values, we can extract optimal policies. Q-learning converges to optimal policies even in complex environments. It's sample efficient for discrete action spaces. Fourth, we'll explore policy gradient methods that directly optimize action selection. Rather than learning value functions, then deriving policies, learn policies directly. Policy gradient methods update parameters to increase expected reward. They handle continuous action spaces naturally, unlike Q-learning. Fifth, we'll understand the exploration-exploitation trade-off. The optimal policy sometimes requires trying inferior actions to learn if they might be better. Balancing exploration, trying new things, and exploitation, using known good actions, is central to RL and often determines performance. After today, you'll understand how learning can happen through rewards and interaction. Let me formalize the RL framework. It has several key components. An agent is the learner. It takes actions and learns. The environment is everything else. It responds to actions and provides feedback. The agent can't directly control the environment. It can only influence it through actions. Separation between agent and environment is fundamental. State is the agent's observation. In chess, it's the board position. For a robot, it's sensor readings, camera images, joint positions, force sensors. In a video game, it's the game screen. The state should contain all information relevant for decision making. Actions are the agent's choices. In chess, moves. For a robot, joint movements. In video games, button presses. The action space can be discrete, finite distinct actions, or continuous, infinite possibilities. Discrete is easier for learning, but less flexible. Continuous is more realistic, but harder to learn in. Reward is the feedback signal. In chess, rewards come at the end. +1 for win, 1 for loss, 0 for draw. For robots, you might reward forward progress, penalize energy consumption. In games, collect point rewards. The reward signal defines what the agent optimizes for. Good reward design is crucial. Poor rewards cause unintended behaviors. The transition model describes how the environment evolves. Given state and action, what's the next state and reward? Sometimes the agent knows this model-based RL. Often it doesn't and must learn through experience, model-free RL. Policy is the agent's strategy. Deterministic policies map states to actions. Stochastic policies assign probabilities to actions. The goal is finding policies that maximize cumulative rewards. Reinforcement learning typically assumes the Markov decision process MDP framework. An MDP is a tuple SAPRG. S is the state space, A is the action space. PSSA are transition probabilities. Given state and action, the probability of reaching each next state. RSA is the reward function, immediate reward for action in state. G is the discount factor, 0, Taylor, G, she 1, determining how much we value future versus immediate rewards. The Markov property is crucial. The future depends only on the current state and action, not on the history of how we got there. Given the current board position in chess, the probability of winning depends only on that position, not on the moves leading to it. This property enables efficient learning. We don't need to remember entire histories. The Markov property doesn't mean the environment is deterministic. PSSA can assign probability to multiple next states. Many real environments satisfy the Markov property approximately. Partially observable environments where the agent doesn't see the full state violated, but extensions like partially observable MDPs, POMDPs, handle this. Solving an MDP means finding the policy maximizing expected cumulative reward. Given perfect knowledge of P&R, we can solve with dynamic programming. Given only experience, we learn through trial and error. Value functions estimate how good states are, how much cumulative reward we can expect. The state value function Vs under policy P is the expected cumulative future reward starting from state S and following P. In chess, Vs for a winning position is high. For a losing position, Vs is low. Vs depends on the policy. Following a good policy yields higher values. The action value function QSA estimates expected reward for taking action A in state S, then following the policy. Q values answer how good is this action in this state. They're more specific than state values. They condition on the specific action. The Bellman equation expresses values recursively. The value of a state is the immediate reward plus the discounted value of the next state, Vs, add saying ERS, PS, plus GVS. This is powerful because it relates values of different states. It enables computing values by solving systems of equations or by iterative updates. Optimal value functions V, false, and Q are values under the optimal policy. They satisfy V as was max A, Q as A, and Q S A was E R S A plus greevy S. Knowing QQ, we extract the optimal policy P S was argmax AQ S A. The beauty of value functions, once we have them, optimal policies follow immediately. So RL algorithms often focus on computing value functions, deriving policies afterward. Q-learning is one of the most important and successful RL algorithms. It learns optimal action values directly from experience. The key insight, after taking action A in state S and receiving reward ER and next state S, we update QSA. The target is R plus Gmax AQSA. The received reward plus the discounted value of the next state under the optimal action. We move QSA toward this target by a fraction A learning rate. Q-learning is off policy. It learns about the optimal policy while following any exploration policy. The agent can explore randomly or follow an E-greedy policy, mostly exploit, sometimes explore, and Q-learning still learns about the optimal policy. This flexibility is powerful. The algorithm is simple. Maintain a Q table, state action values. Each time you take an action and get feedback, update that entry. As you gather more experience, Q estimates improve. Policies derived from Q values improve too. Eventually, Q estimates converge to Q and the greedy policy becomes optimal. Why does Q learning work? The key is the bootstrap. We estimate QSA using QSA. This is learning from yourself. Though Q estimates are initially wrong, the Bellman equation eventually ensures convergence if you explore sufficiently. Given infinite experience, Q-learning converges to Q, regardless of the exploration policy. Q-learning works well for discrete action spaces where you can maintain a Q table. For continuous actions or very large state spaces, approximations like deep Q networks use neural networks to approximate Q values. Q-learning requires a Q table with one entry per state action pair. In video games with pixel observations, there are more states than atoms in the universe. Infeasible to maintain explicit tables. Deep Q networks use neural networks to approximate Q values. A network takes state and outputs Q values for all actions. With pixels as input, this requires deep convolutional networks. Training proceeds like supervised learning. Compute loss between predicted Q values and targets. Update network weights. Experience replay stores transitions in a buffer. During training, sample random batches of past transitions, not just the latest one. Why? Recent transitions are correlated. If you suffer a crash, many consecutive states lead to bad outcomes. Training on correlated data is inefficient. Random batches break correlations, enabling efficient learning. Policy gradient methods learn policies directly without explicitly computing value functions. Rather than maintaining Q tables or value networks, maintain a policy network. Given a state, the network outputs action probabilities, stochastic policy, or action values, deterministic policy. The goal: update parameters to improve the policy. The policy gradient theorem gives the direction to update. The gradient of performance with respect to policy parameters is proportional to a nabla log pi, a vertical bar SQS, A. This means increase the log probability of actions with high Q values, good actions, and decrease the log probability of low Q value actions. The algorithm collect experiences, compute Q values from rewards, compute gradients, update parameters. Policies improve slowly, unlike Q learning, which can improve abruptly, but are more stable. Why use policy gradients instead of Q learning? First, continuous actions. Q learning requires discretizing or complex optimization over action space. Policy gradients handle continuous actions directly, output continuous action values from the network. Second, stochastic policies can be optimal in some environments where deterministic policies fail. Third, policy gradients often learn more stable and smooth behaviors. Actor-critic methods combine both. The actor, policy network, generates actions. The critic, value network, evaluates actions. Critic guides actor training. This synergy is powerful. Critic provides stable learning signals. Actor handles exploration and continuous actions. One of RDEL's defining challenges is the exploration-exploitation trade-off. Exploitation means taking actions you know are good. If you found a restaurant with excellent food, you keep going there. Short-term, this maximizes your satisfaction. Exploration means trying new options. You might discover an even better restaurant. Short-term, you might have disappointing meals, but long-term, you might find better places. The tension: optimal long-term behavior sometimes requires short-term, suboptimal actions for exploration. Without exploration, agents converge to local optima. Without exploitation, they never accumulate reward. Simple approach: epsilon greedy. With probability, epsilon, choose a random action. Explore. With probability 1 minus epsilon, choose the best known action. Exploit. As learning progresses, decay A towards 0. Explore less as you gain confidence. More sophisticated approaches. Softmax treats good actions with higher probability, but still explores alternatives. Upper confidence bounds, UCB, balance estimated value and uncertainty. Uncertain actions get bonus exploration probability. Optimism. Under uncertainty explores actions whose upper confidence bounds are high. The exploration-exploitation problem appears everywhere, not just RL. Online advertising balances showing proven ads, exploitation, versus new ads, exploration, to learn which performs best. Recommendation systems balance recommending familiar content versus novel content. Drug testing balances known treatments versus experimental ones. The key insight: some exploration is necessary and the right balance depends on the problem. Too much exploration wastes reward. Too little misses better strategies. Temporal difference learning is the core mechanism enabling practical RL. TD learning updates values based on other estimated values, bootstrapping. This differs from supervised learning where targets are known labels. In RL, we don't have targets, only estimates. TD uses these estimates. The TD error D equals R plus gamma V of S prime minus V of S measures prediction error. Received reward R plus discounted estimated next value gamma V of S prime minus current estimate V of S. If delta is positive, we underestimated. Update VS upward. If delta is negative, we overestimated. Update downward. TD combines advantages of two classical approaches. Monte Carlo collects full trajectories, then updates values using actual returns. Advantage, unbiased estimates. Disadvantage, must wait for episode completion, high variance. Dynamic programming updates immediately using bootstrapping. Advantage, sample efficient, low variance. Disadvantage, requires model biased. TD learns online from individual transitions without waiting for episodes. Combines MC's online learning with DP's bootstrapping. TD also uses the model implicitly learned through experience. TD typically converges faster than MC and more efficiently than DP. Different TD algorithms differ in how they use bootstrapping. TD0 uses one-step bootstrap, VS prime. TD lambda uses multi-step traces blending bootstrap horizons. N-step methods use n steps of actual rewards, then bootstrap. These variations trade bias and variance. Policy iteration and value iteration are classic RL algorithms when the model is known. Policy iteration alternates two steps. Policy evaluation. Given current policy PI, compute its value function, V, by solving the Bellman equation. Can use dynamic programming sweeps. Policy improvement. Extract better policy P prime by greedily choosing best actions given values. If pi prime differs from pi, repeat. If pi prime equals pi, the policy is optimal. Policy iteration converges. Value iteration simplifies by combining both steps. Do one-step Bellman backups. V of S left-hand arrow max AE of R of S, comma, A plus gamma V of S prime. Repeat until convergence. Extract optimal policy greedily. This is simpler conceptually and computationally than policy iteration. Both algorithms are guaranteed to converge to optimal policies given finite state/action spaces and access to the model. The value action pairs satisfy Bellman optimality equations. V star S equals max AE open bracket R open parenthesis S comma a close bracket plus gamma V star S prime close bracket. Why discuss these if we can't use them directly? They provide theoretical grounding. Understanding policy and value iteration clarifies why TD learning, Q learning, and policy gradients work. They're the theory underlying practical algorithms. In problems where the model is known or easily learned, they can be applied directly. When multiple agents learn simultaneously, the complexity increases significantly. Single agent RL assumes a stationary environment. Multi-agent RL has non-stationary environments. Other agents' policies change as they learn. Your greedy exploitation assumes other agents' values remain constant, but they change. This breaks convergence guarantees. Game theory addresses this. A Nash equilibrium is a strategy profile where no agent benefits from changing strategy unilaterally. In a Nash equilibrium, each agent's strategy is optimal given others' strategies. But finding Nash equilibria and learning toward them in complex games is challenging. Cooperation versus competition creates different dynamics. Cooperative multi-agent RL has agents with aligned objectives. They coordinate to maximize shared reward. Competitive RL has agents with opposing objectives, win-loss games. Mixed scenarios have both cooperative and competitive relationships. Practical approaches, independent learners, where each agent learns its own policy, ignoring other agents. Works surprisingly well, but ignores useful coordination. Centralized training, decentralized execution where agents share learning but act independently during deployment. Communication where agents exchange information to coordinate. Shared reward structures aligning incentives. Applications, multi-robot teams cooperating on tasks. Autonomous vehicles navigating shared roads. Multiplayer game A, I like Alpha Star, StarCraft 2. Recommendation systems with multiple stakeholders. Multi-agent RL is a rich research area with many open problems. Reinforcement learning powers impressive real-world applications. Game playing represents RL's most visible success. AlphaGo defeated world champion Lee Sedol in 2016. AlphaZero learned chess, shogi, and Go from self-play, mastering each in hours, surpassing human grandmasters. These achievements convinced many of RL's potential. Games provide clear reward signals and environments useful for developing RL algorithms. Robotics applies RL to physical control. Robots learn manipulation, picking objects, assembling in-hand object reorientation. They learn navigation, exploring environments, avoiding obstacles. Learning in simulation, then transferring to robots, sim to real, addresses sample efficiency, but faces domain gap challenges. Real-world RL is sample inefficient but increasingly effective. Autonomous vehicles use RL for motion planning and decision making. Self-driving cars must decide actions in complex traffic scenarios, accelerate, brake, change lanes, optimizing for safety and efficiency. Real-world deployment requires extreme robustness due to safety-critical implications. Recommendation systems optimize for long-term user engagement using RL. Traditional systems maximize immediate click probability. RL enables sequencing recommendations considering future engagement. This is subtle. Optimizing for engagement without manipulating users or promoting poor content is challenging. Other applications: power grid optimization, chip design, drug discovery, protein folding. AlphaFold uses RL, portfolio optimization. RL scope continues expanding. Despite impressive achievements, RL faces important challenges. Sample efficiency remains a critical limitation. A human learns to play chess or drive in hours. RL agents require millions of samples. For autonomous vehicles or robots, collecting this much data is impractical or dangerous. Improvements include meta-learning, learning to learn faster, knowledge transfer, and model-based methods that learn environment models to reduce required interactions. Sim to real gap. Simulators aren't perfect. Learned behaviors in simulation don't always work in reality. Friction coefficients differ slightly. Sensor noise differs. Actuator characteristics are approximate. Domain randomization trains in varied simulations, hoping this variance helps real-world transfer, but perfect transfer remains elusive. Safety is paramount in critical applications. Exploration means trying untested actions, potentially dangerous in self-driving cars or medical robots. How do you safely explore in high-stakes domains? Constrained RL learns policies respecting safety constraints. But formal verification of safe exploration is unsolved. Reward specification is subtle. Defining rewards that incentivize desired behavior without creating perverse incentives is hard. Reward hacking, where agents exploit reward specifications in unintended ways, is common. Human feedback, learning reward functions from examples, inverse RL, inferring rewards from expert demonstrations, and value alignment research address this, but remain open challenges. Tomorrow is day 8, Advanced AI Applications and Ethics. We shift from pure technical content to deployment and societal aspects. We'll explore real-world AI deployment challenges. Academic problems and industry problems differ dramatically. Real-world systems must handle data drift, concept drift, adversarial examples, and distribution shifts. We'll discuss production machine learning, monitoring systems, and continuous improvement. We'll tackle AI ethics and fairness. Algorithms can amplify historical biases. Decisions affecting people's lives, loans, jobs, criminal sentencing, medical treatment, require ethical consideration. Fairness metrics, bias detection, and ethical frameworks are evolving. We'll explore these complex issues. We'll cover privacy-preserving AI. Federated learning trains models on distributed data without centralizing personal information. Differential privacy adds noise-enabling statistical analysis without revealing individuals. Privacy AI trade-offs are nuanced but increasingly important. AI safety and alignment address ensuring AI systems behave as intended. Specification gaming, where systems exploit specifications. Reward hacking, where systems behave perversely while technically achieving specified rewards. Specification robustness is an active research area. We'll discuss AI's future, opportunities in healthcare, science, education, risks from misuse, concentration of power, job displacement, governance, regulation, and responsible development. Excellent work today. You now understand decision making through reinforcement learning. Tomorrow, we explore the broader context of AI deployment, ethics, and societal implications. See you then.